Hey guys, so we're looking at 3.2 today. I actually already recorded this lecture, and then when I was looking at my video, I realized that for some reason it did not record the first two examples that I was talking about really well. So I'm going to try recording this again, and let's hope it works this time. So in this section, we are looking at how to find zeros for our polynomial functions, which basically means we're trying to see how we can solve our polynomial functions, and finding their zeros is basically the same thing as finding their roots or x-intercepts. So basically, if we say you have a polynomial function p of x, and this is looking at this first paragraph over here. So if you have p of x, which is a polynomial function, then basically any value of x that you find such that it ends up giving you 0 as your answer when you put it in your polynomial function, those values of x are actually what we call as the zeros or the roots, which, like I said, you can also think of them as being the x-intercepts of your polynomial functions. So just as an example, if you look at this polynomial here, you've got p of x equals x squared minus 9. So if you look at x squared minus 9 as your polynomial function, then if you take the numbers positive 3 and negative 3 and put them back into your function, replace your x with positive 3 or negative 3, you are actually going to get 0 as your answer, which tells you that 3 and negative 3 are what we call as zeros of this polynomial function. And if you look at the graph of the p of x equals x squared minus 9, you will see right here at positive 3 and negative 3 on the x-axis, our graph is crossing the x-axis, and that's where your function values or your y values are going to be 0. So those are what we're talking about when we say 0 of the polynomial function, okay? So for anything which is a degree 2 polynomial, like our quadratic functions, or degree 1 polynomial, which could be our linear functions, finding those zeros or the roots are pretty simple and straightforward. But once you get in higher degree polynomials like degree 3 or higher than that, then those techniques do not work, and so we have to actually look at some different methods. And a lot of times what happens is you don't have just one single method of looking at it. You may actually have to combine different theorems and different rules to narrow down your answers, and then maybe hopefully come up with some possible solutions that you would have. So the first thing we're going to be looking at is what we call as the remainder theorem. Remainder theorem basically says if you take your polynomial function p of x and divide it by some expression which is x minus c, x of course is going to be your variable and c will be some number. So whatever remainder you get after you are done with this division, it will actually be similar to if you took that number c, put it inside your polynomial function, and the answer you get is going to be that same answer r as the remainder of your polynomial if you did a division. So that's what we're actually going to be looking at here in example 1. So they're asking us to use the remainder theorem, and they're saying find p of 1 if your given polynomial function is x squared minus 7x plus 9. So what happens here is, you actually have to divide by x minus c. So you have to take this polynomial function and divide it by x minus c. So if you're dividing it by x minus c, that c value, that number c, is actually going to be this number 1 that they're giving us right here inside this parentheses here. So you're going to be actually dividing it by x minus 1 instead of x minus c. But this worked out pretty well because your number 1 was a positive number, so it stays as x minus 1. But what if they had asked you to find something like this, p of negative 2? So if you are given a number which is negative, then when you put it in this x minus c format, that negative with the negative sign from the x minus c, the two negatives actually end up becoming positive, and you end up getting, x minus negative 2, which will end up become x plus 2. So you kind of have to be careful about what sign this number will have, and then based on that, we will know what we are dividing by. So let's go ahead and take a look at how we can use this remainder theorem to see what this value comes out to be when we try to find P of 1. So when they're asking us to use the remainder theorem on this first example, you actually have to use long division to find what your answer is going to be. So you are actually going to take this expression of x squared minus 7x plus 9, and we're going to be dividing it. Remember, when you are using P of 1, that means you are dividing by x minus 1. Okay? Now, I don't know if you guys remember long division or not, but it would look something like this. So let's say you were taking the number 7 and dividing it by the number 3. So you would try to find if 7 goes evenly into 3, or what's the closest number that would go into it, right? So we know 3 times 2 is 6. So we can multiply 3 times 2, get a 6. Then we would subtract these two. 7 minus 6 would end up giving you a remainder of 1. And this, of course, would be your quotient. Okay, so we're going to use the same idea here with our long division, except we're working with polynomial functions and not just with an x value. So you will see our first term here is x squared, and the first term here is just an x. So if I'm going to subtract x squared, I need to have an x squared down here, right? Which means for this x here in my divisor, I actually need to multiply this by another x, because x times x here will end up giving us x squared for our division. And then you're also going to take this -1, which is part of your divisor, and also multiply that with the x. So -1 times x will give you -x. But then remember, in division, when you're doing long division, we need to subtract both of these numbers. So that means my positive x squared will actually end up becoming negative, and my negative x will end up becoming positive here. So when you do the cancellations, or when you basically bring this together, this positive x squared will now cancel out with this negative x squared, and then your negative 7x is being added with a positive x. So -7 plus x will end up giving you -6x here. Go ahead and bring down this +9. Okay, so now I have a -6x here, and I have just an x over here, which means to get rid of this, I should have a -6 in my quotient. So again, you're going to multiply your divisor. X times -6 will give us -6x. -1 times -6 will give you +6. And then again, in division, since we need to subtract these guys, negative times negative, this guy ends up becoming positive. Negative times positive will end up becoming negative. So again, -6x, +6x will cancel out. +9 minus 6 will end up becoming a +3, and this is going to be our remainder. And then remember, this guy, of course, is our quotient. Okay, now if we want to verify that the answer we came up with is correct, we can do a little check where we're actually going to find out what does P of 1 give us if we substitute this into our original polynomial function. So let's find out what P of 1 is. Our expression is x squared minus 7x plus 9. So that's x squared minus 7x plus 9, which will end up giving us, you know what? Let's do this here. This will give us 1 minus 7 plus 9. 1 minus 7 is -6. -6 plus 9 is 3. And you will notice this is the same number as our remainder, where we got 3 when we did the long division. So this is exactly what this remainder theorem is talking about. If you took your polynomial p of x, divided it by x minus c, the remainder you got r is going to be the same thing if you did this little substitution here, and you should get that same answer of r. Okay, so that's what this first example here is talking about. So I hope that kind of makes sense. Okay, now let's look at a different way of division. So sometimes instead of using the long division, you can actually use what we call as synthetic division. So synthetic division, and you can kind of see I've shown you the comparison here. Synthetic division actually works a little bit faster than the long division, and your textbook is actually calling it the ordinary method of dividing polynomials, or basically the ordinary division. So ordinary division is just another term for long division, and you can see this is the same example that we did in number 1, so you can compare your answer here. So this is the same thing. Now I want to show you how you can use synthetic division for the same example and what kind of answer you come up with. So let's get back, and I'm going to show you right here on this same page here how to do synthetic division. So synthetic division, let's go ahead and write down our polynomial expressions here. So our original polynomial is x squared minus 7x plus 9, and we are trying to find p of 1. So in synthetic division, what you do is we start out by drawing this little half box or semi box, whatever you want to call it. And then we actually take our coefficients from our polynomial. So the x squared has a coefficient of 1. My middle term is -7, and my constant term is +9. And you will see there are no missing terms here. So that's a good thing. If we had missing terms, we would need to put zeros for them. But for now, we've got our x squared term, x term, and the constant term, so none of them are missing. So just take the coefficients and write them down. So we've got x squared, which has a coefficient of 1, our x term, which is a coefficient of -7, and then your constant term is a coefficient of 9, and they're asking us to find p of 1. So with synthetic division, if they're giving you the number 1 specifically like they are here, you're going to take that same number 1 and you're just going to bring it down, and that's what we're going to be dividing by. So the way synthetic division works is you take that first number and you just bring it down as it is. You don't multiply, you don't change it in any possible way, just bring down that 1 as it is. Now you're going to take this number 1 and multiply it by the number we're dividing, which also happens to be a 1. So you're going to multiply 1 times 1, and that gives us an answer of 1, and you're going to put that 1 right here. -7 is going to be added with the 1, so it's -7 plus 1, which gives us -6. Then again, we're going to take this -6 and multiply it by this divisor of 1 again. So it's going to be -6 multiplied by 1, which will again give us -6. And then you are adding 9 minus 6, which will give you 3. And 3 again is going to be our remainder. And you will see this is the same answer we got when we did our little check with the substitution, or when we did our long division, we got the same answer of 3. And then this number here, which was the first two numbers, these are actually going to be part of your quotient. So the way it works is, since our original polynomial is a second degree, it's an x squared polynomial, your quotient is always going to be 1 degree less than the original polynomial you started out with. So since my polynomial is x squared, our quotient is actually going to be an x term. So that's going to be x minus 6. And if you go back to the long division, you will see that's exactly what we had for our quotient. Here, we had x minus 6. So you can see the synthetic division is still going to give you the same results as the long division does, but look at how many fewer calculations we had to worry about in synthetic division than we did with long division. So that's why, we talk about how the synthetic division goes faster than the long division. And again, you can compare the calculation that I just did here in your handout. So just remember that, and I have this underlined here, that since we are dividing our polynomial by x minus c, that's why the degree of your quotient is always going to be one less than the degree of your dividend. Dividend is basically the polynomial term in this case that we're looking at. Okay, so how about we look at example 2 and see how we can use our synthetic division again to find the quotient and the remainder for this expression here, which is x to the third power minus 7x plus 5, and it's being divided by x plus 2. So let's go back here, and this is our second example. So we've got x cubed minus 7x plus 5 divided by x plus 2. So in this case, you will actually notice that my x squared term is missing. So we've got our x to the third, but there's no x squared term. So to hold its place, I'm actually going to write it as 0 times x squared. And you know 0 times anything is 0, so we're not really bringing a new term. We're just holding a place for it. And then I've got my minus 7x plus 5, okay? And then they are asking us to divide this by x plus 2. So for our synthetic division, I think I did that bigger than I wanted to. Okay, so let's write down our coefficients from our polynomial. So x cubed will have a coefficient of 1. For our missing term of x squared, we're going to put a 0. Then you have minus 7 for the x term, and then our constant term is 5. Now they're asking us to divide by x plus 2. So for the x plus 2 term, remember this is the same thing as our x minus c. So in this case, it would be x minus negative 2, which means the number you're actually dividing by is going to be negative 2. So always go with the opposite sign than what's given to you if they give it to you as x plus 2 or x minus 1. Now, if they just give you p of 1 like they did in the previous example, then you can just use the number 1 itself. So in this case, since they're telling us it's dividing by x plus 2, that means the number you're actually dividing by is going to be negative 2. So as I showed you for the previous example, that first number, you just bring it down as it is, okay? Then multiply 1 with negative 2, which will give us negative 2. Add 0 and negative 2, so that adds up to negative 2. Again, we are multiplying negative 2 with negative 2. So negative times negative will become positive. 2 times 2 is 4. Then we add the numbers on the inside, so that's negative 7 plus 4, which is negative 3. All right. Again, you're going to multiply negative 2 times negative 3. So 2 negatives become a positive. 3 times 2 is 6. And then 5 plus 6 will give you 11. So again, 11 is going to be our remainder. And then these numbers here will be part of the quotient. So again, guys, remember our polynomial is a third degree polynomial, which means our quotient is going to be 1 degree less. So if polynomial is third degree, quotient is going to be second degree. So this is 1, which means my coefficient here should be 1. So that's my 1x squared or just x squared. Minus 2 will go with x, so that's minus 2x. And then minus 3 will be your constant term. So for our result, they wanted us to find the quotient and the remainder by using synthetic division. So your quotient is x squared minus 2x minus 3, and the remainder is going to be the number 11. Just keep in mind, when they ask you to write down the quotient and the remainder, remainder is going to be this last number here, but quotient, you need to bring back your variable. So if you're using x as the variables in the original polynomial, then you should have x in your quotient. So just don't write 1 minus 2 minus 3 as your answer. You have to write it as x squared minus 2x minus 3. So I hope this kind of makes sense to you of how that synthetic division works compared to our long division. All right, guys, I hope this was helpful. So they are saying to find the value of the polynomial p of x for x equals c, they're saying we can divide the polynomial p of x by x minus c, or you can basically just substitute the value of c for x, and you can do your computation. So that would basically be just putting in whatever this number c is for the x value in your polynomial and just go solve it that way. Now they are saying using long division to divide by x minus c is not an efficient way to evaluate a polynomial. And I think that's just because it can take a pretty long time for us to simplify a long division. So that's why we do actually prefer synthetic division over the long division method. Because it's going to take less arithmetic operations to solve that, and also it is actually better than the substitution method also. So you will see that for most of these examples, we are going to use the synthetic division. All right, we've got another example here, guys. So they are saying use synthetic division to find p of 3 if p of x equals x cubed plus x squared minus 9. So let's take a look at this example here. Okay, so you should notice again that we do have a missing term. I have x to the third power. I have x squared, but the missing term is the x term. So again, for that x term, you can write it as 0x and then minus 9. And let's get our little synthetic division problem going. So this would be a coefficient of 1 for the x cubed, coefficient of 1 for x squared, our missing term, so that's going to be the 0. And then we have negative 9 for our constant term, and they're asking us to divide by 3 because they're asking us to find p of 3, right? So in this case, since the number 3 is given to you, you're just dividing it by this number 3 here. So again, remember, bring down that first number as it is. You don't have to do anything to it. And then we start multiplying. So you're going to do 1 times 3, which is 3. Now we're adding the 1 plus 3, which will give us 4. Now multiply 4 times 3. So 4 times 3 is 12. 0 plus 12 would of course be 12. And then you are multiplying 12 times 3. And 12 times 3 will of course end up giving us 36. And then you are doing negative 9 plus 36. So if you subtract 9 from 36, you of course get an answer of 27. So 27, the last number, is always our remainder. And then these first numbers are part of the quotient. And since we have a third degree polynomial as our original polynomial, the quotient will be 1 degree less. So our quotient will start at x squared, and that's a coefficient of 1. So that's going to be 1x squared, or just x squared, plus 4x plus 12. Okay. Now, in this example, they were not asking us to find the quotient and the remainder like example 2 was. Here, they wanted us to find what the value of p of 3 is going to be. So the value of p of 3 is actually going to be 27, because remember from our remainder theorem that we looked at on the first page, the remainder is always going to equal your polynomial evaluated at that value that you divided it by. And you can do a quick check again. So if you wanted to do a quick check, you can take your p of 3 and put it in your original polynomial. So that's x to the third power plus x squared minus 9. So of course you're looking at, oh, sorry, this should be the third power. You're looking at 3 to the third power, so that's 3 times 3, which is 9. 9 times 3, which is 27, plus 2. Oh, I don't know what I'm doing, do I? This should be a 3 here, because my x value is 3. So this should be 3 to the third power, which is 3 times 3, which is 9. And then I have my constant term minus 9 at the end. So of course you should see this plus 9 minus 9 will end up canceling each other out, and they give you the answer 27. So the substitution, you can do that as a check like we did here, but when they're asking you to find P of 3 for the given polynomial, you do want to use synthetic division, and then this is the answer we are looking for. Okay? So as you can see, that synthetic division goes by pretty quickly as compared to our long division does. Okay, so that was looking at the remainder theorem. Now we want to look at the factor theorem. So they are saying, okay, again, we have a polynomial here, x squared minus x minus 6. They can say we can find the zeros of the function by taking that polynomial x squared minus x minus 6 and setting it equal to 0 and then trying to factor it. So if you're trying to factor it, basically you are looking for two numbers that will multiply to give you -6, which is our constant term, and then adding to give you -1, which is our middle coefficient. So in this case, we know either 6 times 1 or 3 times 2 will give us 6. So it has to be 3 and 2 because 6 and 1 do not work in this case. And then the idea is, since we want -1 to be our sum, when we add the two numbers, that means my 3 has to be negative and my 2 has to be positive. So when I multiply, I get -6. When I add the two numbers, I get -1. So that's where this x minus 3 and x plus 2 is coming from. Take each factor, set it equal to 0, and then you end up getting x equals +3 and x equals -2. Now these two numbers are going to be zeros of our polynomial function. If you take the number 3 and -2 and put it back into your polynomial function for x, you will get zeros as your answer. And then they're telling us each factor of the polynomial has to correspond to a 0. So which means from each factor, you should always get one of the zeros, or basically x-intercepts of your polynomial function. So the factor theorem here is talking about the number c is a 0 of your polynomial function, p of x, if and only if you take the expression x minus c, and you can show that it's going to be a factor of your polynomial. So if the number c is a 0 of your polynomial function, then that means x minus c, that expression, is going to be a factor of your polynomial function. And so that's kind of a neat theorem to look at, again, when we're trying to solve these polynomial functions. So they're saying synthetic division can be used in conjunction with the factor theorem. So again, you can use the synthetic division to help us work through this factor theorem. They're saying if the remainder, when you divide your polynomial function by x minus c, is 0, then that means you're of course going to get a 0 for that number, and we would say c is a 0 of your polynomial function. So they're actually kind of repeating what I just talked about right now. And then remember, x minus c will be a factor of your polynomial function. Okay, so how can we use this factor theorem to help us out? So looking at example 4, they are talking about, so let's say we're giving you the expression x minus 1, and they want to know, is x minus 1 a factor of our given polynomial function, which is this guy here, x cubed minus 3x plus 2. So the idea is, doesn't matter if you use long division or synthetic division, if x minus 1 is a factor of this polynomial, then your remainder should be 0. And that's kind of what they're talking about here in this little paragraph. So again, let me say that one more time. If x minus 1 is in fact a factor of our polynomial, then you should get a 0 remainder. So let's take a look at this example 4 right here. Okay, so let's go to our notepad. So let's rewrite this polynomial. We've got x to the third power. Of course, you'll see we're missing the second power. So that should be 0x squared, then minus 3x plus 2. And they want to know if x minus 1 is a factor, which means we are dividing by x minus 1. But since we're using synthetic division, we only need the coefficient. So for x to the third power, your coefficient is 1. For our missing term, we'll put a 0. Coefficient on our x term is minus 3. And then our constant term is positive 2. Now we are dividing by x minus 1. Remember, you go with the opposite sign from the x minus 1. So since that's a minus 1, that means you are actually dividing by a positive 1. So again, take that first number and bring it down as it is. Then we're going to multiply 1 times 1, which will give us 1. 0 plus 1 is 1. Okay? So again, take this 1, multiply it by our divisor 1. So that's 1 times 1, which will again give us a 1. Negative 3 multiplied by, sorry, we're adding here. I apologize. That's negative 3 plus 1, which will actually give you negative 2. And then negative 2 multiplied by 1 will give us negative 2. And then when you add 2 and negative 2, you end up getting 0. And this is what we were hoping for. So if x minus 1 was a factor, then yes, we should have had a 0 remainder. And since we have a 0 remainder, you can basically say, yes, x minus 1 is a factor of this polynomial. So your instructions were saying, if x minus 1 is a factor, then we want to factor p of x completely, which means you need to find the other factors also. And that's where this quotient part actually comes into play. So let's see how we can find the other factors. So you have a third degree polynomial as your original polynomial. So remember, your quotient is going to be 1 degree less than that. So since this is third degree, our quotient is going to be a second degree polynomial. So that's going to be x squared from here plus x from the middle. And this guy will be our constant term of negative 2. So again, 1x squared or just x squared plus 1x or just x, and then minus 2. Now we're actually going to need to factor this little quotient portion. So let's go ahead and factor this guy. So you are looking for two numbers that multiply to give us negative 2, but add up to give us positive 1. Now, of course, there are only two numbers which will multiply to give you 2, and that's going to be 2 and 1. But since we need our sum to be a positive 1, that means your 1 is going to be negative, 2 is going to be positive. So when I multiply 2 times negative 1, I get negative 2 as my answer. When I add 2 and negative 1, I get positive 1 as my answer. So your factors here will be x plus 2 and x minus 1. And now to write your factors all together, your answer or your solution here is going to be this x minus 1 that we were proving if it's a factor or not. You're going to have that. And then I'm going to take these two factors from our quotient and put them together as well. So you can write it like this, or if you'll notice, these guys are the same. So you can also write it as x minus 1 to the second power multiplied by x plus 2. And this is your complete answer that they are looking for. So the first part was just to check and see if x minus 1 was a factor, which is what we showed by using the synthetic division. And if you got 0 remainder, then yes, this was a factor, and we proved that. Then you took the quotient that we got from that synthetic division and you tried to factor it again, and that guy factored into x plus 2, x minus 1, and then you take all three of these factors and you put them together. Okay, and that's how you get your final answer. So the three factors together, but since these guys are the same, you can write them to the second power and get your final answer looking like that. Okay, so now guys, the idea is if you take each one of these factors, set it equal to 0, you will find the zeros of your polynomial, or basically the x-intercepts for your polynomial function. Okay? Alrighty, very good. So the next part that we are looking at is the fundamental theorem of algebra. And this is a pretty straightforward theorem. So if you look at this little first paragraph here, we're saying, does every polynomial function have a 0? So we're basically saying, can you find a solution for every polynomial function? And basically, Carl Gauss, sometimes you'll hear people call him Carl Gauss, but mostly we've heard it called as Gauss. And that's how my instructors used to say that name, so that's how I say it. So Carl Gauss basically proved the fundamental theorem of algebra, which is based on this idea of every polynomial function has a 0 or not. And he actually did that as part of his doctoral thesis at the age of 22 in the year 1799. So I thought that was a pretty neat fact about, how young he basically got his PhD. So that was kind of neat. So your basic fundamental theorem of algebra is saying if your polynomial function has a positive degree, then that polynomial function will have at least 1 0 in the set of complex numbers. Now, when they're saying in the set of complex numbers, they're actually also including imaginary numbers in there. So they are saying that the 0 that you find for your polynomial function could be a real number, but it could also be an imaginary number. And you will see that as we look at more examples as we move forward in this section and this chapter. Okay? And here's a neat fact. If you have an n degree polynomial, then you should have at most n number of zeros. So if it's a third degree polynomial, you will have a maximum of 3 zeros or 3 factors to your polynomial. If it's a fifth degree polynomial, then at the most you will have 5 zeros for that function. So that's kind of a neat rule to kind of keep in mind. And they're also telling us that the fundamental theorem will also tell us that a polynomial function has at least 1 0, which is what we just saw in this little definition box here. But unfortunately, the fundamental theorem of algebra does not tell us how to find it. So this is where we're actually going to be looking at a bunch of different techniques to see how we can find these zeros for our polynomial functions. And so we're going to be running into quite a few different theorems as we keep working through these examples. Okay? So they are saying the zeros or roots that are rational numbers, you can think of them as being rational zeros, are the easiest to find. So rational numbers, remember, are again numbers that can be written in the form a over b. So that's why they're calling them rational zeros, because it could be a number that basically looks like a fraction and not just an integer. So this rational zero theorem is basically saying you take your leading coefficient, which will be from that highest degree term in your polynomial function. So you take the coefficient for that highest degree, and then you take your constant term, which will be the one that has no variable on it, right? It will be just a positive or a negative number that they give you. So they are basically saying you're going to take the first coefficient of your polynomial function and the last coefficient of your polynomial function, and you are actually going to set it up where you take the factors for the constant term, which is what we're calling as p, and divide it by the factors of your leading coefficient term. So you're basically going to take the factors of this constant number, a sub 0, and you're going to divide it by the factors of your leading coefficient, which is a sub n. And if you're a little bit confused about what exactly they're talking about here, you will see when we do our example, it will actually end up making more sense for you. So let's take a look at this example here. So we are given 6x squared minus x minus 35. And you will notice here, they actually just went with factoring. So they took our polynomial expression and factored it into 2x minus 5, 3x plus 7. They're taking each factor and setting it equal to 0. Solving for x, you move 5 to the other side, divide by 2, and you get x equals 5 halves. You get 3x plus 7, so move the 7 to the other side, divide by 3, and you end up getting negative 7 over 3. So the way they actually got this was they took the factors of 35 and they took the factors of 6. Now 6, of course, will be factors of 1 multiplied by 6 or 2 multiplied by 3, right? So you can actually write this as 1, 2, 3, and 6. And same thing with 35. 35 can be 1 times 35, but you can also have 5 times 7. So you can write that as 1, 5, 7, and 35. So if you look at these two factors that you came up with, you have 5 over 2. So that's the 5 that's coming from here, which is from the 35. The 2, which is coming from the factors of 6. Your negative 7 is actually coming from here. So that's the 7 with the negative sign, and the 3 is again coming from the factors of 6. So both these factors are coming from those coefficients, you know, if your constant term or the leading coefficient. And so rational zero theorem actually kind of uses this idea, and we'll get into a little bit more detail of where that negative sign came up with when we get into our example here. But basically they are saying the rational zero theorem does not identify exactly which rational numbers are going to be the zero. It only gives us the possibilities. What that means is once we go through this idea of the rational zero theorem, it's only showing you what all the possible answers can be, but it can actually give you a lot of choices. So sometimes it can give you 2, 4, sometimes it can give you 6, maybe even 12 different options. And the idea is you have to know that not all of those are going to be the zeros for our polynomial function, but those are some of the possibilities. So those answers could be possibly our solution, but that does not necessarily mean it is going to be, or that all of them are going to be. So it's a little bit of a guessing game at this point, because you know the higher you get into your polynomials, the more difficult it becomes to solve them. All right, so let's see how we can use our rational zero theorem to solve a problem like number 5 over here. So let's go to our notebook again. All right, so for number 5, we are given 2x cubed plus x squared minus 4x minus 3. Okay, so remember for the rational zeros, and this is asking us to find the possible rational zeros, you are only going to be using the constant term and the leading coefficient term. You don't need any other of those middle terms, okay, for the rational zero theorem. So we are going to take all the positive factors of that constant term 3, and we are going to look at all the positive factors of that leading coefficient 2. So of course for number 3, you know 3 is only a product of 1 times 3. 2 is only a product of 1 times 2. So you don't have too many options in this case. Now, what you actually end up doing, remember, these are going to be the constant term is what we call as the p values, and then the leading coefficient factors are what we call as the q. And let me show you where we know that from. That's where they were giving us p over q, where p is a factor of the constant term and q is a factor of the leading term. Okay, so that's where I'm getting my p and q variables from. So the way we calculate the possibilities for the rational zeros is by looking at this ratio where you're taking p divided by q. So each of these p values, which is 1 and 3, has to be divided by each of these q values. So the way I set this up is I go ahead and start out with my 1 and 3 from the top, and I'm going to be dividing that 1 by 1 from my number 2, dividing my 3 by the 1 also, and I'm going to rewrite that 1 and 3, but this time I'm going to be dividing it by 2. So remember, each value of p has to be divided by each value of q. So that 1 and 3 has to be divided by 1, and then the 1 and 3 has to be divided by 2. So this is our initial setup. Now, all the possible rational zeros are actually going to have both positive and negative signs. So that means 1 over 1, of course, you can write it as 1. 3 over 1, you can write it as 3. And then these guys will stay as 1/2 and 3/2. So that means you can have positive and negative 1, which is coming from here. You can have positive and negative 3, which is coming from here. You can have positive and negative 1/2, which is coming from here. And of course, you can have positive and negative 3/2, which is again coming from here. So even though you are seeing 4 options here, by the time we put these positive and negative signs, you end up getting twice that many, which means we have 8 different options. So what we are saying for this polynomial functions here, 2x cubed plus x squared minus 4x minus 3, out of these 8 possible solutions, any one of them could be a 0 for this polynomial function. And you know what? Sometimes, and you will see this as we move forward, only one of them may be a solution, or sometimes not even a single one of them could be a solution. So it's a pretty interesting thing when you think about how these work out to be. All right, so let me do a quick recap. You take your constant term of 3, break down into its factors, which is 1 and 3. Then you take your leading coefficient, which is 2, and again find its factors, which is 1 and 2. And then you're going to take the factors of 3, which is what I'm calling the letter p, and you're going to divide each of those factors by the factors of 2, which is what I'm calling q. So it's p over q. So 1 divided by 1, 3 divided by 1, and then 1 divided by 2, and 3 divided by 2. So 1 divided by 1 is the same thing as 1. 3 divided by 1 is the same thing as 3. And then you have your 1/2 and 3/2. And then for the final answer, they should have both positive and negative signs. So positive negative 1, positive negative 3, positive negative 1/2, and positive negative 3/2. These are going to be all the possible rational zeros that this polynomial could have. Okay. So what's going to happen now is basically now we have all the possibilities now, but how do we know which one works and which one does not? Because remember, we're still trying to find the zeros for our polynomial functions. Now they can be rational numbers, they can be irrational numbers, or for that matter, they can also be imaginary numbers, because if you end up getting a negative inside like a square root, right? So the easiest way to do would be to take each number in the list of your possible rational zeros and basically use synthetic division to see which one of those will give you 0 remainder, or you could basically use substitution, so plug those numbers into your polynomial and see which one of those gives you a 0 answer. Or they're actually also talking about looking at a graph of a polynomial functions and see on which numbers your graph is crossing the x-axis, and then those could be your zeros also. So for number 6, this is actually the same example that you just looked at in number 5. So they're asking us to find all the possible zeros, and so we're basically going to be checking all those 8 options that we got in number 5 and using that to see which one of these will give us 0 as a remainder. So let's go over to our notepad over here, and basically remember we are checking which one of these numbers are going to work. So all our possible rational zeros from number 5 were positive and negative 1, positive and negative 3, positive and negative 1/2, and positive and negative 3/2. So let me show you. We don't have any missing terms here, so that's good. We can start out with our positive 1. So I'm just starting with that first number and looking at the positive, and write down your coefficients. So that's positive 2, positive 1, that's negative 4, and negative 3 from our polynomial function. So remember, this first 2 comes down as it is. Then you're doing 2 times 1, which is 2. Add, so 2 plus 1 is 3. 3 times 1 is 3. I'm adding negative 4 with 3, which comes out to be negative 1. And then negative 1 times 1 is negative 1. And we get an answer of negative 4. So this is not a 0 remainder, which means this guy is not a 0. So cancel that out because he didn't work out, right? Okay, now let's check that against negative 1. The same coefficients, 2, 1, negative 4, negative 3. Bring down that first 2 as it is. So bring down that 2. 2 times negative 1 is negative 2. Then you're adding 1 plus negative 2, which comes out to be negative 1. Again, multiply negative 1 with negative 1, which gives you positive 1. Then you are adding negative 4 with positive 1, which gives you negative 3, right? Then negative 3 times negative 1 is now going to be positive 3. And when I add negative 3 with positive 3, I get a 0 remainder. So if you're getting a 0 remainder, then yes, this is actually one of our zeros, which means we're going to keep him, right? So that's our negative 1. So negative 1 worked. Now, basically the idea is you have to go through your checklist and check for all of the other numbers. So what I would say is, just as a practice, go ahead, pause this video and look at all the other options and see out of the remaining 6 options, which ones are going to work as our rational zeros and which ones are not going to work as our rational zeros. And then you can come back and start the video again and check your answers against mine. So go ahead, pause your video. Okay, so I actually went ahead and did the positive and the negative 3, and you will notice that both positive and negative 3 did not give us any 0, so those guys were canceled out. Now I actually wanted to show you, just in case you are confused of how these fractional numbers would work when you're doing synthetic division. So I actually wanted to talk to you about this one. So same thing, start by bringing down this 2, and then you would multiply this 2 that we just brought down with this divisor, which is 1/2. So basically that ends up giving you, if it helps, you can write it over 1. So that ends up giving you 2 over 2, which gives you an answer of 1. So you would actually be bringing that 1 here, and then you would add 1 plus 1, which gives you 2. And then of course you're back multiplying 2 with 1/2, which is the same calculation that we just did. So 2 times 1/2 gives you 2 over 2, which will again give you an answer of 1. So bring that 1 over here. Then you're adding -4 with 1, which will give you -3. So now we are multiplying -3 with the 1/2. Again, if it helps, write it as a fraction, -3 over 1. So this will end up giving you -3 over 2. And this will not reduce. Do not convert these into decimals. Leave it as -3/2 and bring it up here. Now we are supposed to be adding the -3 with -3/2, right? So you're adding these two numbers. So you would again need to find a common denominator or use your calculator to do this. But basically you would end up multiplying this guy by 2, which would then give you -6 over 2. And you are adding a -3 over 2 with that, which would of course end up giving you -9 over 2. But basically the idea is you knew you were not getting a zero remainder. So since this guy is not a zero, that means +1/2 doesn't work for us. And then you can try the same thing with -1/2. So again, I would say the same thing. Pause the video, go ahead and try. Okay, so as you can see, I went ahead and did the others also, and you can kind of see some of the scratch work that I have down here. So we already saw that +1/2 did not work. Now you can see -1/2 does not work out either because it did not give us a zero remainder. -3/2 also did not give us a zero remainder, but look at this. +3/2 gave us a zero remainder. So this one, you can see out of those 8 options that we had, only 2 of them worked, which is still really good. So you had 3/2 that we're checking. So bring down that 2, multiply 2 times 3/2, which is what I've done right here. So 2 multiplied by 3/2 will give us 6/2, which reduces down to a 3. So we bring that 3 over here. 1 plus 3 is 4. 4 multiplied by 3/2 will end up giving you 12 over 2, which reduces down to a 6. So that gives you the 6 here. Adding -4 with the 6 gives you +2. 2 multiplied by 3/2 is the same calculation we did here. So that gives you a +3. And then -3 added with +3 gives you a zero remainder. So in this case, the possible zeros that will work for this polynomial here are -1 and +3/2. So the zeros for this polynomial are -1 and +3/2. So this will be our answer here for number, what was it, 6? Yeah, number 6. Okay, so there you go. And I hope you guys at least tried some of these examples so you were at least able to get some practice in. Okay. All right, let's come back to our handout over here. So I've actually given you quite a bit of space there, looks like. And then they're telling us when you have a quadratic polynomial, it is best to try and see if factoring will work or use a quadratic formula to find your remaining zeros. So we can actually take a look at that as we look at this example 7 here. So for example 7, they're asking us to find all the real and imaginary zeros for this polynomial function, which is 3x to the third power minus 2x squared plus 12x minus 8. Okay, so let's take a look at how we can find these zeros for this polynomial function. So this is this example 7 right here. Okay, so I'm actually going to start by finding my rational zeros first. Okay, so let's look at the factors for this leading coefficient of 3 and this constant term of 8. So let's start out with the positive factors of 8. So 8 can be 1 times 8 or 2 times 4. So you can actually write those as 1, 2, 4, and 8, right? Same thing for 3. We'll look at the positive factors of 3. And 3, of course, is just going to be 1 and 3. So remember, this is our P, this is our Q. So when you're trying to find those rational zeros, we divide P by Q. So I'm going to take each number of my P term, and I'm going to divide it by Q. And since I have two numbers for Q, I'm going to write these guys twice. And then the first ones I'm going to be dividing by 1, which is my Q term here. And then the second one I'm going to be dividing by 3. And then you can use commas to separate all these answers, right? So all the possible rational zeros are going to be positives and negatives of this number. So 1 divided by 1 is just going to be 1, so that's plus or minus 1. 2 divided by 1 is just going to be 2, so that's plus or minus 2. 4 divided by 1 is 4. 8 divided by 1 is 8. So those are our positive and negatives for the first fraction we did, or division we did, sorry. And then same thing here, positive and negative 1/3, positive and negative 2/3, positive and negative 4/3, and positive and negative 8/3 for that last one. So these are 1, 2, 3, 4, 5, 6, 7, 8, 16 total possible zeros, and that's going to be a long checking for us to do. So to save you some time, we're not going to be checking all 16 of them because trust me, we'll be here forever. So I'll go ahead and tell you that out of all these 16 options, there's actually only one rational zero that's going to work out to be. And we're going to use synthetic division to check for that. So the only rational zero that works is going to be, and of course I'm going to make you wait for it, aren't I? So let me go ahead and write my polynomial coefficients here. So I've got positive 3 from my leading term. We've got negative 2 from the x squared term. I've got positive 12 from the x term, and then negative 8. And you will see there are no missing numbers in there. Okay, so the rational zero that's going to work out of all 16 is actually going to be 2/3. I know, not a happy number, but you will be fine. So start by bringing that first 3 down, and then we're going to be multiplying 2/3 with 3. I'm going to do my scratch work here on the side. We're going to take the number 3 and multiply it by 2/3. Again, if it helps, you can write it over 1. Now you can multiply 3 times 2 and get 6 over 3. Or the other thing you can do is 3 and 3 are going to cancel each other out, and you get an answer of 2. So this guy will become a 2. Then add negative 2 and positive 2, which will end up giving us 0. 0 multiplied by anything is 0. So you know 0 times 2/3 will become 0. So this guy will be 0. 12 plus 0 is 12. Then we are going to multiply 12 times 2/3. Again, if you want, you can write it over 1. Now again, you can multiply 12 times 2 and then divide by 3, or you can see that 3 goes into 12 4 times, and you can do 4 times 2, which will give you 8. So this guy will become an 8, and 8 and negative 8, when you add them together, give you 0. So you can see we got a 0 remainder, and that's how we know 2/3 is going to be one of the rational zeros that we can use. So that means you have actually only found one answer so far. And this is a third degree polynomial, which means there is a possibility we should have two more answers, and that is actually going to come from right here. So we're actually going to use this quotient to help us find the other solutions, or the other zeros basically. So since this is, again, remember, a third degree polynomial, that means our quotient is going to be a second degree polynomial. So that will become 3x squared. Since that's a 0, that means your x term is a 0 plus 12. So you can actually write this guy as just 3x squared plus 12. And we need to actually solve this quadratic equation that we have to find the other zeros for our polynomial function here. So this is where we were talking about you can use the factoring method, you can use the quadratic formula, or honestly, you can also use the square root property to solve this. So let me show you how we can find our other solution. So we are going to take our quotient and try and solve it. So let's solve our quotient. So that's 3x squared plus 12. And since we're trying to find the zeros here, basically set this quotient equal to 0. So the first thing you're going to do is start by moving that 12 to the other side, just like you're solving an equation. So move that 12 to the other side. You get 3x squared equals negative 12. And then we want to get x by itself, or in this case, x squared by itself. So divide by 3. Those guys cancel out, leaving you with x squared. And then 3 goes into 12 how many times? Negative 4. So you will have x squared equals negative 4. And this is where that square root property is going to kick in. So to get rid of that square on the x squared function, you're going to have to take a square root. And remember, with square root, you get one positive and one negative root. So the square and square root will cancel each other out on the left side. You will get x equals plus or minus. Now remember, you need to simplify the square root of negative 4. If you remember, we had talked about this in the previous chapters. So you can think of this as being negative 1 times 4. If you want, you can separate this as square root of negative 1 and square root of 4. Now, square root of negative 1 will, of course, become your I, and square root of 4 will become 2. So this guy will actually end up simplifying into 2i. So you end up with positive or negative 2i, and these guys are going to be your other zeros. So we've got positive and negative 2i from here, which is when we solve the quotient, and then initially, from all the possible rational zeros that we had, we got 2/3 also as one of our zeros. So the zeros for this function are going to be the 2/3 that we started out with, and then the positive 2i and the negative 2i we got when we simplified our quotient. Okay, so look through this example, and of course let me know if you have any questions. But that's kind of what we are talking about in this section right here, just looking at all the different ways that we can find the zeros. So we of course looked at the rational zero theorem, which is the last thing we did here. So we talked about the rational zero theorem. We of course talked about the fundamental theorem of algebra, the factor theorem, and then of course the first thing we talked about was how you can use that remainder theorem to even come up with these possibilities of what the solution can be. And then we looked at long division and synthetic division to help us out. Okay, guys? So let me know if you have any questions, and I will see you in class the next time. So take care. Bye bye.